Thanks for staying on to listen to me today, talk about the Christchurch Town Hall. A bit of background about me. I was actually in Vancouver when the earthquake struck in Canterbury and moved back in 2012 and took on this project in about 2013 during the sort of concept phase. I was keen when I came back to Canterbury to learn as much as I possibly could from the Canterbury earthquakes, and it's been a really great environment to be in for the last 10 or so years, just to soak up that knowledge and learn lots. We were obviously absolutely ecstatic to win the not only the Heritage Award but the Joint Supreme Award for this project, which demanded a whole lot of the structural engineers who worked on it. And yeah, pretty amazing project to work on. So today I'll just talk about a bit about the project background, a bit of the history, some of the post-earthquake damage observations that we saw, a little bit about the analysis and design, and some of the highlights I think from the construction that I thought were pretty cool. So one of the things that's a bit special about this project is that back in the 1960s, Sir Miles Warren and Maurice Marnie teamed up to do the architectural. They won basically the architectural competition to design the Christchurch Town Hall. The story goes that they sat down at a dining room table and developed the concept over about a week, won the competition, and then after that, Lyle Holmes, who is the originator of Holmes Consulting, he was brought on board as the structural engineer for that project. So it was pretty cool that we got to team up with Warren and Marnie on the re-engineering piece, or the post-earthquake piece. So a bit about the actual building complex. So I'll talk a little bit today about this. So 5 buildings or 6 buildings, depending on how you count them. But you've got the auditorium here, the foyer space where you come in, the James Hay Theatre. Down here is the Limes room, and down here is the kitchen. So those 5 buildings were built in the 1970s, and then about 10 years later, there was the Cambridge room was added on into this. So as for building structural forms go, the auditorium's got a lot of walls that go to ground. Likewise, James Hay Theatre, same sort of thing, very stiff with a lot of walls. Same thing with the kitchen down here. Now, probably unsurprisingly for a foyer and a large open space, we've got frames for the foyer and frames for the Limes room down here. So flexible, sandwiched in between relatively stiff structures. Now the building consists of mostly reinforced concrete. It's a mix of precast and in situ construction, and a mix of normal reinforced concrete as well as some post-tensioning involved. Now, one of the big challenges for this project is that it's all on display. So the brittleistic architecture is a lot of the structure, and the structure is all on display. So relatively challenging, and it was listed as a local heritage site, and now it has New Zealand heritage status. So one of the things that's really interesting is we have on file the calculations, specs, drawings that are all scanned and from back in the day. And what's really amazing is you see all the assumptions that were made to get the design to work. So lots of mechanics, lots of assumptions. So you can see the earthquake coming in from the right, and how they developed the understanding of what the building was doing. It's been really helpful having those documents on file, so that we go back and work out what was intended, so that we could develop the strengthening solution. What was really interesting about this project is, well, this was being designed, there was a lot of research going on at Canterbury at the same time, so you do start to see in some of the detailing, more stirrups and some of the ends of beams and things like that. So end of promenade beams, you started to see some increased stirrups, which suggests that they started getting a bit of an understanding for things like capacity design. So Canterbury earthquakes. So when the September 2010 Darfield earthquake occurred, there was actually a refurbishment project going on at that time, and they were working on the building, but actually there was a rapid assessment done, and there was relatively little damage. Unfortunately, the February 2011 earthquake was a lot closer, and there was widespread liquefaction and lateral spreading that affected the building. What's really interesting is there wasn't a whole lot of shaking damage in the building. It was primarily, a lot of the issues that we found were that the liquefaction caused the building to have to take up or adopt a new displaced shape due to the ground underneath it moving and shifting and sinking. So if we take a cross section through the auditorium structure and a bit of understanding as to what had happened. So when the earthquake happened, there was the liquefaction, and if the Avon River is down to the right, down here, there was liquefaction, lateral spreading, and the building sort of did roughly this in a shape. So there was 600 mils of total settlement and around 300 mils of differential settlement from one side of the auditorium to the other. Now, what does that cause to the building? So there was a whole lot of, well, not a whole lot of, but there was a significant cracking in the ends of these promenade beams where the heavy internal walls moved down relative to the relatively lightly loaded external columns. And so it caused the cracking in the beams, which is all on show. Now, there were non-structural elements such as block walls that basically got crushed when the structure moved down, and the hogging of the slab basically got crushed. So you saw some of these pictures. What was really interesting when you went and did observations at the building was that the stairs, which you can just see in the side here, when you walk down those stairs, you actually felt like you're walking up because of this hogging in the slab. So it was a really unusual sensation to be walking downstairs, but kind of walking up at the same time. Another part of the structure, so the limes room, again, Avon River down here. What was really interesting about this part of the building was that a geotechnical failure of or sort of slip circle occurred. So it tilted up, kind of surfed down towards the river with significant displacement along that. So from one end of that building to the other, there was about 300 mils of displacement. And because that structure is relatively linear, it was quite easy to see. So we'll talk a little bit about that later, what we did about that. What do we see? So at the roof level, when it pulled away and sort of went down towards the river, the roof sagged. So you can see I had to go and put some temporary propping in there. There was actually a seismic separation at the floor level, but that wasn't enough, and obviously wasn't prepared for what actually happened. And all around the site, we had this spalling damage to lots of double T's. It's fairly common. So one of the other really interesting things that we observed was anything that was relatively lightly reinforced, intersecting with a large column or beam that had significant strength or stiffness, there was significant damage occurred at those. So the crack meter, you're measuring off the centimeter scale rather than the fractions of a millimeter scale. What this caused was widespread flooding. So you can see there's a whole lot of water that occurred in the basement. There was basically about a meter of water in the basement that we needed to pump out when we had to go and do damage assessments. So what do we have to do with that? So the basic brief starting off was, all right, we've got this damaged building. Please return it to what it was. So we want to have this structure. Please take it from that point to the other one, and along the way, can you strengthen it to strengthen it as well? So part of that, part of the early concepts, we developed two things. We did nonlinear time history models within the answer program, and used those to further our understanding of these buildings. So they are relatively complex, and obviously a lot of the detailing doesn't comply with the new standards. So we're able to use things like ASC 41 to classify joints and beams and columns and things to basically push the structure and target the strengthening to it. What was also interesting is we actually had some of the records, obviously, of the earthquake that occurred, albeit that the Canterbury earthquake was 11 seconds of strong shaking versus what we need to do for a scaled to 1170. So a little bit of a video just of what you see when we run the nonlinear time history. I think this is El Centro, and the distortion is obviously turned up, so it doesn't quite move that far. kind of gives you an idea of what you can start to see when you look at these models. So one of the things I mentioned just before was that we developed a Revit model in tandem with some of the analysis models. The Revit model was extremely useful for communicating with all the different stakeholders that we had to communicate with. So people like heritage advisors, the council was a big one. Being able to display things in 3 dimensions and communicate those ideas was hugely valuable to getting them to understand the significance and different options that we were considering along the way. Now, it's pretty well publicised that the ground under the town hall, and I've already mentioned, is pretty poor. So one of the really key areas of design that we worked hard on was the soil. So Tonkin and Taylor were partnered up on this one, and the basics of it, of what we developed. We developed 2 main solutions, one of them being piles with ground beams, and the second one was jet grouting underneath with the raft solution. So in the end, we decided on the jet grout in the raft solution. So in basics, that you go in and put a whole lot of jet grout piles in, interlinked, and creating this sort of honeycomb structure. And then we come along and put a raft solution in there. So that was the concept. There was a lot of work that went into what needed to be done in detailed design. So for those of you who haven't worked with jet grouting before, you're basically creating a hole and then putting a probe down, and you're shooting out cement and water and air at a high rate of knots, and you create all these unreinforced sort of soil columns that roughly have about 2 MPa of strength, and you overlap them, so you're kind of creating a bit of a secant wall sort of solution, and that stabilizes the ground improvement for that structure. So that's all well and good, but how do we do that when we've got an existing building? We learned a bit more about that as we moved on. So the basics of jet grouting were that if there's a soil particle in the middle of the cell, it is essentially confined, so it can't, you can't liquefy the soil if it can't go anywhere. So the general grid that TNT came up with as a concept solution was about 6 by 6, and what they were trying to aim for was a 30% replacement ratio. So 30% of the soil would be jet grout, and the other 70% could remain as the normal soil. And this is what it kind of looks like. This is actually the finished one that was done by the contractor. So zooming in a bit, you basically have a whole lot of interlacked jet grout columns, creating that honeycomb structure, and also placing these jet grout columns underneath the height loaded parts of the building. And then in cross section, the rough what we had. So we had the liquefiable soils, and we were basically bringing these jet grout piles down to bear on that, and then bearing our foundation, our rough foundation on top. One of the challenges that we had was that a lot of the subcontractors had different equipment for building these jet grout columns. So we knew that we had Tonkin and Taylor come up with the overall concept of the ground improvement, and we could design the raft slab and make sure that the superstructure could accommodate that. But there was a bit of an unknown here with the contractor. So how big are the columns going to be? So there was significant work done to understand the performance and the bounds of that solution. So you can see over here, this is the Plexus model from Tonkin and Taylor. They did their own sensitivity analysis, saying, what if we get big columns at larger spacing versus small columns with closer spacing? What does that mean for what we were doing? And we did similar things. We bounded our analysis with our REM concept, looking at soft springs and hard springs, and looking at what the behavior was. So there was significant collaboration with Tonkin and Taylor to understand the likely performance and make sure that the solution that the contractor came up with was within the bounds of what we wanted for the structure. So one of the things that was really interesting was that once we put the raft into the nonlinear time history models, it actually solved a lot of the issues that we were having that were sort of displacement related. One of the ones that we couldn't solve straight off the bat without intervention was this really interesting one around the promenade, where the beams that had been designed or built in there were had too much flexural steel, so they were causing a shear failure in the main part of the beam. Now, if you remember earlier, with the damage that occurred in these beams, we actually had quite a lot of cracking in the ends of these beams, and so to kill two birds with one stone, we developed a solution where we actually did some selective weakening of these beams, so that, and then FRP strengthened the ends of these beams so that they could go through the earthquake, so that the shears were reduced in the center of the beam, so we didn't have to intervene in this part, and we had to repair this part of the joint anyway. And now if you walk into the site, you'll notice that it's fairly obvious when you look up, because you can see that something's happened, but that's basically what we did there. Now, for the foyer and the limes room, I mentioned earlier that they were quite flexible. So in the foyer, we did come up with a few different concepts of how we might strengthen the building, but the one that won out was actually just rebuilding. So all of these columns in the foyer were rebuilt with compliant reinforcing. One of the things that's quite interesting, you have this big heavy box, and you've got these with columns about their minor axis underneath. And what happened was the load obviously wanted to head out towards this, so we ended up having to clamp that function room back to back into these columns. Limes room was a bit different. We not only rebuilt the columns, but we actually put some BRB braces in to help that structure out. And obviously they were still quite flexible, so we had to account for not only creating some seismic gaps, but also accounting for where the structure would be after releveling for the limes room, but also if there was any deformation, we could account for that. So there's lots of surveying and accounting for that in the detailing. So construction highlights. So some of the things that that I think were quite cool with what happened when they built it. First up was the jet grouting. So I showed earlier the big picture of the rig. Yes, there was a really big rig, which they used primarily on the outside of the building. So this guy here, they were able to build the columns really quickly with that rig. And in the tight spots, they had these mini ones. So they brought a few different pieces of kit out from Germany, because it was Keller and Browne Civil that did this work. Probably unsurprisingly, it's very messy. There was a lot of jet grout, cement around the place, and sort of, you got these guys walking around in quite a lot, kind of going, "Oh, this is a heritage building," and it's got very messy. So a lot of the interesting things also were related to the how. So how do you go in and re-level parts of the structure? How do you go and rebuild columns? So we developed some of these pieces during the communication phase. These end up on the drawings, but on the final set. But this was the part of the communications piece of how do we do this. One of the things that was very advantageous was that a lot of the pad foundations were about a couple of meters down below ground. So we were building the actual raft up at a higher level. We were able to have the building supported on its original pad foundations that had jet grout underneath it whilst we did our thing. So partially building the raft, prop the building, and then rebuild and things. So that part was really interesting. Now a separate team at Holmes worked on the temporary works in conjunction with Hawkins on it. So they did have access to our models, and they had access to the understanding of it, and developed some really cool solutions of how do we do some of this work. So we had to rebuild a piece of this block wall at the back of the James Hay Theatre, and they developed this frame which was supported on the raft. And that's this frame here. It's about 19 meters long. So when this was above the ground, it was pretty amazing to look at, to be honest. That photo doesn't really do it justice, just how big that was, as that sat up above the ground for a period while they did work underneath. Now, one of the really interesting pieces, I think, as well, was when we decided that we were going to re-level the limes room. So they demolished the columns underneath and then propped them up on these temporary V frames. And then as we had a number of aftershocks and the Kaikoura earthquake come through as part of that timing, we needed to make sure that we could lower this building, but also make sure that if we had any lateral loads in it, that it wasn't going to slide on into the river. So they came up with some really clever detailing to achieve that. And we've actually got a video time lapse on the next one, which I'll just start here. So this is when the re-leveling started. You can see it was lifted at the back and lowered at the front. So opening day, both in the 1970s and in 2019 were both significant days for the building, I think. So in 1971, you can see the photo on the left, there was people right around the corner down Colombo Street who wanted to come in and see the structure, see this building that was so significant for Christchurch. Same thing happened in 2019. There was a lot of people who turned up for the opening. What I found really amazing was just walking around and seeing how many people just enjoying being in the building. So I think a lot of the time we forget the significance of what we do and how it affects the community and how it affects, you know, people who have memories of concerts there and significant moments. I know I walked across, as probably many engineers did, across the stage to get my degree back in the day. So it was really cool just seeing people sitting in the auditorium. They had music playing on opening day and just enjoying the space, enjoying the atmosphere.
Yes, Mark from John Snook here. David Hopkins asks, interesting time history shapes. What were the boundary conditions of the structure? How much of the soil was modelled as acting as structure?
Try to understand that. How much of the soil was structured as acting with the structure? So we had models where where Tonkin and Taylor provided us what the soft response of the combined soil was likely to be, as well as the stiff end of the response. So we ended up having to run the model for both ends. We had gap elements which represented the behaviour of that, and there was significant back and forth between what the RAM model was telling us and the time history to make sure that the appropriate grillage, I guess, and representation of those soils were interacting. For the actual, we didn't go and model the actual ground improvement. We modelled, I guess, the expected performance of the ground improvement underneath.
Mark, there's a couple of other questions. What's the cost of ground improvement jet grouting solution compared to total strengthening cost?
That's a good question. I don't have actual figures. I understand it was in the region of 15 to 20 million, I think, but don't quote me on that. Relative to the strengthening cost, I think the total strengthening reported is 167, but keep in mind that the total extra number actually added in, there was added scope. So there was what I didn't talk about was the added CSO building that replaced the Cambridge room. So that was in the overall final cost.
Two people have asked similar questions. Oscar Wang says, does this new seismic strengthening meet the current code and standard? And Brendan Donald asks, were you strengthening to 100% NBS?
Yeah, so when we built new elements, I'll start with, yes, we strengthened it to 100% of design basis earthquake, and because you have existing you've got existing columns with existing detailing, you don't theoretically meet code standards, but what you're able to do with ASC 41 and things is make sure that the performance meets the targets of the 100% MBS. If there was new elements, say like the rebuilding of the columns, we made sure that the confinement and flexural reinforcement and everything that complied with 3101.
And David Hopkins has followed up with another question. So there was a break between soil and structure in your model, question mark.
There wasn't a way. I view it probably more as an overlap. So there was modelling done by Tonkin and Taylor to represent what the structure was doing in their Plexus model. and we would represent the bounds of their response. So in my mind, I feel like you don't have a model that's necessarily got the soil, the raft, the superstructure all doing their thing at once, but what you're trying to do is represent the two and bound them and overlap them and make sure that there's nothing that that's going to kind of catch you out. So whilst you don't necessarily have them in the same model, we definitely tried to model the different expected performances, I'd say. So there was a significant, we spent quite a lot of time over at Tonkin and Taylor, and Tonkin and Taylor spent a fair bit of time, and we definitely compared notes and made sure that, that we understood what each other was doing in that design piece.
Mark, David Hopkins has said thank you for a most informative presentation. So perhaps if I could step in on behalf of Michelle, who's had to leave, and thank you from all of us for, yes, a very informative presentation. Thank you from those present and also from all of CSOC. And once again, congratulations on the awards which you won. Thanks. You for your time. Thank you, Mark.
Thanks, everyone.